NENOMATICA, where mathematics meets YouTube excellence. Scientific notation. Welcome to our math lesson about scientific notation. Today, we're going to learn how to work with very large numbers in a way that makes them easier to understand and manipulate. Let's start with an interesting question. Do you know how long the Earth's circumference is at the equator? The Earth's circumference is approximately 40 million meters or 40,000 kilometers. That's a very large number to write out, 40 million or 40,000,000. When dealing with very large numbers like this, it becomes cumbersome to write all those zeros. That's where scientific notation comes in handy. Scientific notation allows us to write numbers in a more compact form. A coefficient between 1 and 10 multiplied by 10 raised to some power. Let's convert the Earth's circumference to scientific notation. We start with 40 million or 40 million meters. To convert this to scientific notation, we need to move the decimal point until we have a number between 1 and 10. Moving the decimal point 7 places to the left gives us 4 times 10 to the power of 7. So the Earth's circumference is approximately 4 times 10 to the 7th meters, or equivalently, 4 times 10 to the 7th meters. Now, let's look at another interesting problem. If each ant is 1 millimeter long, how many ants would we need to form a line around the Earth at the equator? We already know that the Earth's circumference is 40 million meters. Since each meter is equal to 1,000 millimeters, we need to multiply by 1,000 to find the circumference in millimeters. So let's multiply 40 million meters by 1,000 millimeters per meter. 40 million times 1,000 equals 40 billion. In scientific notation, that's 4 times 10 to the power of 10 millimeters. Since each ant is 1 millimeter long, we would need 40 billion or 4 times 10 to the 10th ants to go all the way around the Earth. That's a lot of ants. Can you even read this number? 40 billion has 10 digits and 10 zeros. This is where scientific notation becomes really useful. It helps us work with very large numbers in a more manageable way. In practical situations, we encounter very large numbers like these, and even larger ones. If we write these numbers in standard form, it becomes difficult to quickly understand their magnitude or perform calculations with them. With scientific notation, we can easily compare and calculate with very large or very small numbers. Let's see how much easier calculations become when using scientific notation. If we want to multiply the Earth's circumference by the number of ants, using standard notation would be quite cumbersome. But with scientific notation, it's much simpler. We simply multiply the coefficients and add the exponents. 4 times 10 to the 7th multiplied by 4 times 10 to the 10th equals 16 times 10 to the 17th. Here's a useful rule to remember when working with scientific notation. When multiplying numbers in scientific notation, multiply the coefficients and add the exponents. When dividing, divide the coefficients and subtract the exponents. In conclusion, scientific notation is an extremely useful tool for working with very large or very small numbers. It simplifies writing, understanding, and calculating with these numbers, making it a fundamental concept in mathematics, science, and engineering. Now, when you come across extremely large numbers like the diameter of our galaxy or extremely small numbers like the size of an atom, you'll be able to work with them efficiently using scientific notation. Thanks for watching. Welcome to this lesson on scientific notation for very large numbers. Scientific notation is a standardized way of writing very large or very small numbers that would be difficult to read in their standard decimal form. One of the methods for writing very large numbers is using positive powers of 10. For example, 10 to the power of 40 is a very large number. If we wanted to write it using conventional methods, we would need to place 40 zeros after the digit 1. In conventional notation, this number would be written as 1 followed by 40 zeros. No person with a single glance can count these zeros and understand the real magnitude of this number. However, displaying it as 10 to the power of 40 clearly shows the size of this number and makes mathematical operations with it much easier. Any positive decimal number can be written in the form of a decimal number multiplied by a power of 10. We can express this as a times 10 to the power of n, where is a decimal number between 1 and 10, and n is an integer. Let's look at an example to understand this better. Here we have the number 58 times 10 to the power of 6. This equals 58 followed by 6 zeros, which is 58 million. Scientific notation can also be written using the letter E. Here, 58 times 10 to the power of 6 represents the same value, 58 million. Now, let's discuss an important note about astronomical numbers. Astronomers and scientists don't use this extensive power notation in their calculations. In every step, they encounter large numbers with many insignificant zeros. For instance, the distance to Andromeda Galaxy written in conventional form would be about 95 followed by 18 zeros kilometers. Writing this many zeros is impractical. In astronomical calculations, it's often necessary to express measurements in smaller units like centimeters rather than kilometers. If we were to express the previous distance in centimeters, it would have 5 more zeros, making it even more unwieldy. Scientific notation provides a simple solution to this problem. The distance to Andromeda can be written as 9.5 times 10 to the 18th power kilometers or 9.5 times 10 to the 23rd power centimeters. This not only saves space, but also makes calculations much simpler. In conclusion, scientific notation is not just for convenience. It's an essential tool for working with extremely large or small numbers, especially in fields like astronomy, physics, and engineering. Let's look at our first example. We have the number 245,000. To convert this to scientific notation, we need to move the decimal point to get a number between 1 and 10, then multiply by 10 raised to the appropriate power. First, we identify the first non-zero digit, which is 2. We'll place the decimal point after this digit to get a number between 1 and 10. Now we count how many places we moved the decimal point. Since we moved it 5 places to the left, we multiply by 10 to the power of 5. Therefore, 245,000 in scientific notation is 2.45 times 10 to the power of 5. Let's look at our next example, 1,404. Again, we'll place the decimal point after the first non-zero digit, which is 1. We count how many places we moved the decimal point. In this case, it's 3 places to the left, so we multiply by 10 to the power of 3. So, 1,404 in scientific notation is 1.404 times 10 to the power of 3. Our third example is the number 150 million. Following the same process, we place the decimal point after the first non-zero digit, which is 1. Counting the number of places we moved the decimal point, we find it's 8 places to the left. So we multiply by 10 to the power of 8. Therefore, 150 million in scientific notation is 1.5 times 10 to the power of 8. Now, let's look at a more complex number, 26,478,914. Once again, we place the decimal point after the first non-zero digit, which is 2. Counting the places, we find we moved the decimal point 7 places to the left, so we multiply by 10 to the power of 7. So this number in scientific notation is 2.647891 times 10 to the power of 7. For our final example, we have the expression 12 times 150,000. First, let's multiply these numbers to get a single value. Now we can apply the scientific notation process. We place the decimal point after the first non-zero digit, which is 1. We moved the decimal point 6 places to the left, so we multiply by 10 to the power of 6. Therefore, 12 times 150,000 in scientific notation is 1.8 times 10 to the power of 6. To summarize, scientific notation allows us to express very large or very small numbers in a more concise form. The general format is a number between 1 and 10 multiplied by 10 raised to some power. Positive exponents indicate large numbers, while negative exponents would be used for very small numbers. This notation is particularly useful in science, engineering, and computing. We'll walk through several examples of calculations with scientific notation and see how to simplify these calculations step by step. Let's start with our first example. We have 200 times 423 plus 2. To solve this, we start by calculating the product of 200 and 423. 200 times 423 equals 84,600. Now we add 2 to 84,600, which gives us 84,602. Finally, we can express this answer in scientific notation. 84,602 can be written as 8.4602 times 10 to the fourth power. Let's move to our second example. We have 12.8 times 10 to the fourth power times 5 to the sixth power. To solve this expression, we first need to calculate 5 to the sixth power. 5 to the sixth power equals 15,625. Now, we multiply 12.8 times 15,625. This equals 200,000. Next, we rewrite 200,000 as 2 times 10 to the fifth power. Finally, using the product rule of exponents, we add the exponents of 10 to get 2 times 10 to the ninth power. Now for our third example, we'll solve a more complex scientific notation problem. We have 32 times 11 times 10 to the 12th power divided by 44 times 80. Let's begin by multiplying the numbers in the numerator. 32 times 11 equals 352. Now, let's multiply the numbers in the denominator. 44 times 80 equals 3,520. Now, we can simplify the fraction. We can rewrite this as 352 times 10 to the 12th power divided by 3,520. Let's factor out common terms in the numerator and denominator. We can express this as 3.52 times 10 to the second power divided by 3.52 times 10 to the third power, all times 10 to the 12th power. Simplifying the fraction, the 3.52 terms cancel out, and we're left with 10 to the second power times 10 to the 12th power divided by 10 to the third power. Using the product rule of exponents in the numerator, we get 10 to the 14th power divided by 10 to the third power. Finally, using the quotient rule of exponents, we subtract the exponents of 10 to get 10 to the 11th power. In summary, when working with scientific notation, remember these key rules. First, when multiplying powers with the same base, add the exponents. Second, when dividing powers with the same base, subtract the exponents. Third, when simplifying large numbers, convert them to scientific notation by expressing them as a number between 1 and 10 multiplied by 10 raised to the appropriate power. These rules make calculations with very large or very small numbers much more manageable. Welcome to our math video. Today, I'll show you how to write exponential numbers in decimal representation. Let's begin with our first example, 2.28 times 10 to the power of 8. To convert this to the decimal representation, we need to shift the decimal point 8 places to the right. When we move the decimal point 8 places to the right, we get 228 million. Let's look at our second example, 9.4612 times 10 to the power of 9. Here, we'll shift the decimal point 9 places to the right. Moving the decimal point 9 places to the right gives us 9,461,200,000. Our third example is 1.1 times 10 to the power of 4. We'll move the decimal point 4 places to the right. Moving the decimal point 4 places to the right gives us 11,000. Let's look at our fourth example, 1.43 times 10 to the power of 5. We'll shift the decimal point 5 places to the right. Moving the decimal point 5 places to the right gives us 143,000. Our final example is 1.23 times 10 to the power of 6. We'll move the decimal point 6 places to the right. Moving the decimal point 6 places to the right gives us 1,230,000. Let me now explain the general rule for converting a number in scientific notation to decimal form. When we have a number in the form of times 10 to the power of n, we move the decimal point n places to the right when n is positive. To summarize, when converting a number from scientific notation to decimal form, first, identify the power of 10, which tells you how many places to move the decimal point. For positive powers, move the decimal point to the right. The significant digits remain the same, and we add zeros as needed. This is how we get the decimal representation of exponential numbers. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.